So yesterday, there was quite a bit of discussion about how you handle the buoyant force, and from my perspective, it was fun to sit back and listen to the arguments go back and forth. Okay, so let me kind of pose this idea of when you have to consider that buoyant force and when you don't.
I'll take that. Okay.
So let's say that you have a solid brass 100 gram mass sitting on a scale, okay? 100 grams, 0.1 kilograms, right? Multiply that by G, you should get what? 0.98 newtons, right? Cool. Now, technically, is that the true weight of that mass? Technically. Let me ask you this. What if you submerge the whole thing in water? Would that still show up as 0.98 newtons? If you put the whole scale underneath the water?
No.
No. Why?
Force buoyant acting.
Oh, there'd be a buoyancy force acting on it, right? Because that would be the density of water, which is quite large, times the volume of that times G, right? So if you just saw, let's say you didn't see it in air, you just saw it underwater, and you saw that 0.1 kilogram mass sitting on the scale underwater, that might read, I don't know, 0.68 newtons. So if that's all you saw, and you had no reference, you're underneath the water, you'd say, okay, hey, this thing weighs 0.68 newtons, right? But then you take it out of the water, and then what's going to happen to the reading on the scale? It's going to go up, okay? So you all took a balloon, right? And you set it on the scale. And this is what I was doing yesterday. I was trying to get an idea of what your numbers actually were. So when you put, I don't know, whatever balloon it was, and I put that on the scale and it read 2.88 grams. Is that the actual mass of that balloon?
No.
No. Why?
Buoyant
There's some buoyant force acting on it. So the other way that you can view this is imagine that we take that 100 gram mass and we tie a hydrogen-filled balloon to it. If we tie a hydrogen-filled balloon to it, what that reading on the scale might drop from 0.98 to 0.78. So what would be the value of the buoyant force? 0.2. Because if I take that 0.78 and add the 0.2 to it, I get the 0.98 newtons. Now, I want you to visualize this. Imagine that you could take that system that had the scale and your balloon in it, and you could put that into a big vacuum, okay? You could put that whole apparatus into a big vacuum, and you remove the air. What's going to happen to the reading on the scale? It's going to increase. Why?
No more buoyant force.
There's no buoyant force. So the true mass of the balloon, is that bigger or smaller than 2.88? Bigger. Now some of you are flipping out going, oh, the buoyant force is bigger than your gravitational force. You're going, oh, it should go up. Okay? And some of you are flipping out going, we broke physics, because why isn't the balloon going up? But you were basing that off of this being the true mass of the balloon. Is that the true mass of the balloon?
No.
No. The true mass of the balloon is bigger than that. So, you do have a certain buoyant force, right? And you had a certain value there. So how could you actually find the true mass of that balloon? You know, you found the buoyant force, right? And you know the apparent weight of it. If you added those two values together, you would get the true mass of that balloon. And here's the only time that you really needed that. The only time you really needed that was when you were doing the calculation of F equals big G M1 M2 over D squared. Because here's the point. If you use the 2.88, if you use that number in this calculation, again, is that the actual true mass? No. Okay, so if you just use the apparent weight that you got off there, your actual values for the gravitational force is going to be less than what it actually was. So the numbers that you needed for those mass calculations for your gravitational field actually needed to be bigger than this, because what you're getting is a false reading because of the fact that you had that buoyant force. Now, however, when you were actually doing the calculations involving the electrostatic, if you took that 2.88 divided by 1,000 and got the value, you got, where's that at? 0.0282 newtons. Now, in the environment that you were actually doing the lab, that was the actual weight of the balloons in the environment in which the lab was done, because of the fact that that is your actual true apparent weight in the system. So you would use that as the vertical component of those triangles, because in that reality. Now again, think this through. Imagine that you have this setup, and you go, wow, I want a true experiment. And you evacuated the room, okay? You evacuated the air in the room. What impact would that have on your experiment?
They'd weigh more,
They'd weigh more. Why?
because there's no more buoyant force.
There's no more buoyant force. So then your downward force would get bigger, right? Okay? Your downward force would get bigger. Would that make it easier or harder to get those balloons to separate out?
Harder.
It would be harder, because there would be more of a true gravitational field acting down on them. Okay? So that's what I want you to think through. It's like, okay, hey, what's going to happen with that buoyant force? Now, I promise you on the test on Thursday, you will not have to worry about the buoyant force. Okay? You won't have to worry about it. Now, I promise you, are you going to have problems with the triangle and the suspended mass? Absolutely.
Actually, not worried about this. I'm kidding. That's just like.
I'm just going to write the Connor test.
The Connor test,
Yeah.
only triangles?
Just nothing but triangles.
And I like my board.
So, on the test, I promise you, you are not going to have a situation where you have to worry about the buoyant force. Okay?
How long is our test going to be?
It's like any other test. You've taken a lot of tests. They're all about the same length.
Like 2 pages, 3 pages?
Like a few or a couple?
Probably three.
So a few?
Something like that.
It's gonna be like a
worth about
handful
80
of
points.
pages.
There's gonna be multiple choice, there's gonna be stuff you have to work out. So, you know the drill.
Well, I'm just,
Why do you think I'm gonna change how I test for this one versus the
well, no,
other?
I thought there was going to be, so I said 2 or 3. There were 3.
I don't know, I'm not completely done with the test anyway, so there we go. Okay, so let's talk parallel plate capacitors. Kind of important for your existence with phones. Okay? So, if you look at how you calculate, that's Q over, that's a horrible Q.
Wait.
Three meters?
That's millimeters.
Oh, okay.
I'm not off the second.
So that's all you need. That's all you need capacity.
Wait, doesn't distance between them not actually matter?
That's true, but not on the next part.
You should
Changing the rules?
just because.
What's A? You gotta like submerge the
Area.
whole thing in water and
Oh,
like
yeah, that's
shine a light through it and you have to calculate the aim values so you know what's nothing.
No, we are not calculating this, is not
Every 5 or
optics.
so seconds.
Anything can be optics if you're afraid of it enough.
It just sparks like
Everything you see is optics.
Imagine you see this experiment.
Okay, so imagine that you have two parallel plate capacitors. One side is negatively charged, the other one is positively charged. They're 2 centimeters by 2 centimeters. The plate is charged to 20 nanocoulombs. The plate is separated by 3 millimeters. How fast and what direction do you need to launch an electron so that it will just reach the other side and stop? Fetch, can I borrow some paper? So, let's start with this. Let's start with this. So, and Thatch had a good observation. He goes, the distance between them doesn't matter into the calculation of your electric field equation. And it doesn't, okay? But it's gonna matter on the next part when we figure out how we're gonna launch an electron. So it's somewhat, this problem was somewhat analogous to, I'm gonna throw this up in the air, okay? And I want you to calculate how fast I have to launch it so that it goes to a height of 2 meters. So start with something that you know. If I'm gonna throw that up in the air, so it goes to a height of 2 meters, what do you not know?
Initial velocity.
V naught is unknown. What else do you know? What's the final velocity gonna be?
Zero.
The final velocity is gonna be 0. You know your acceleration, which is, right?
Wait, are we doing the throwing up one or the?
No, I'm doing throwing up one as a model,
Oh,
okay?
I was like,
We're gonna use that
okay.
to parlay that into this one. And you wanna know, and if you know it goes up to a height of 2 meters, what variable are you missing? Time. So what are you gonna use?
That equation.
Oh, that equation. V squared equals V naught squared plus 2AD. So it's the same thought process. I'm gonna shoot an electron across this gap. Do you know the distance? I got the distance. Do you know the final velocity?
Yeah.
0, because we just wanted to reach the other side, right? So we know my final velocity is gonna be 0. I got that number. The tricky part is, if I'm in a gravitational field, I know what the acceleration is. I don't know what this acceleration is. That's the tough part.
But you can calculate
Oh, I calculate how?
because you have the,
Two charges.
Yeah.
You can get the field.
you have the
You can
numbers.
get the field and then you can
I
spec
don't
it.
have my equation sheet right now.
Okay, so,
Yeah.
it's the only time that's legal to say that in school. If you can find the field, then you can feck it. So, here's the story. You have to keep it straight, the difference between what the plates are charged to and what the charge is on the particle in between, okay? This Q is not the charge of the electron. That Q is the charge on the plates, okay? Remember that, I did that, took the hand cranked it up, boom, 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 did work, had to separate the charges, okay? So that's this. Your epsilon naught value is going to be your vacuum permittivity constant, which is, of course, I grabbed the wrong one. Somebody's got their, let me see, there's ours.
Right.
So, on your epsilon naught is, let me just start over down here. So you got 20 nanocoulombs. Can you leave that in nanocoulombs?
No.
No,
That's what we want.
Bad.
That is the right course.
Very bad.
bad and,
12 coulombs squared per Newton meter squared. Okay, thank you. So now I've got the 20 nanocoulombs. Nanocoulombs into coulombs is 10 to the negative 9. So if you wanted to shortcut this, you can just write this as 20 times 10 to the negative 9th coulombs. Okay? That's the easiest way to convert from nanocoulombs to coulombs. Is just put 10 to the negative 9th on it. Now, when you talk area, what units does that area have to be in?
Meters squared.
Meters squared, right? So the plates are 2 centimeters on a side. So,
0.004 meters squared, something like that, one sec.
well, do this. Convert the centimeters into meters, right?
Point,
So divide by 100, you get 0.02, right?
I was off the 0. 0.0004.
0.02 meters, and that's gonna get squared,
Yes,
which gets you what?
0.0004, or 4 e to the negative 4th.
Yeah, okay.
Right? Now, look what happens to the units. Your electric field has to be in what units? Because if you look at what Jacob said, and I quote, "We'll just feck it. What units do you want that force to work out to be?" Newtons. You know your charge has to be in what? Coulombs. So the only way this can work out is if your electric field is in newtons per coulomb. So if you look at what happens, these meters squared cancels out, right? You're gonna cancel out one of those coulombs. The newtons is in the denominator of the denominator. The newtons flip up, hey, you get newtons per coulomb. So this kind of wins the award for the most jacked up units. So it actually came out of Maxwell's equations. Maxwell predicted this value, and then they eventually found it. So you're gonna get this number. So somebody run the numbers. Take 20 times 10 to the negative 9th, divided by 8.85 times 10 to the negative 12, and then divide that by 0.0004 square meters. So what do you get as the value of your electric field? Something. Oh my God.
Times 10 to the, what is that?
6.
Right?
Should be something
Yeah,
pretty low.
5.65 times 10 to the 6.
5.65 times 10 to the 6th
Yes.
newtons per coulomb. Now I have the value of the electric field. Now what can I do?
Second.
Now I can feck it. So now I got 5.65 times 10 to the 6th newtons per coulomb. Do I use the charge on the electron, or do I use the 20 nanocoulombs?
Electron, wouldn't you?
Yeah, because I use the electron because that's what's going to feel the force. Because that electron is going to be existing within that field. So what's the charge on any electron?
1.6 e to the negative.
1.60 times
Negative.
coulombs. Miracle of miracles, the coulombs cancel out. You get newtons. Cool. So what do you get out of that for your force?
9.04 e to the negative 13th.
Negative 13. Okay. Cool. Now, I have my force. What's the next step?
Divide by
Acceleration.
Oh, force equals mass times acceleration. What's the mass of an electron?
9.11, e to the negative 31.
So 9.04
Because I
E to the negative 33rd.
times 10 to the negative 13th divided by what was it? 9 point times 10 to the negative
31st.
kilograms, which gets you a huge honking acceleration.
9.92 e to the 17th meters per second.
9 point what?
92. 7. Yep.
Okay,
Delicious.
pretty big number, right?
Gotta go fast.
But you have an extremely small particle, okay? Now what?
Distance equals velocity time. I don't.
No, no,
Christ, Cohen.
E equals V naught one to
that equation, right?
Yeah, that's fine.
What are you solving for?
V. No, V.
Wait,
No, it ends at
Oh, yeah, no.
It ends at zero. Now, but here's an interesting idea.
It's just gonna make it negative.
Which direction is it, are we gonna shoot the electron? Are we gonna shoot the electron from the positive to the negative, or from the negative to the positive?
Against the acceleration, whatever direction that is.
Positive to negative, otherwise it won't slow down.
It's moving against. the
Let's think
acceleration.
about this. Let's just back up for a second.
Wait, isn't it 1.0?
Let's back up for a second. What's the direction of the, forget about the electron. If I just gave you this problem and said, what's the direction of the electric field? What's the direction of the electric field in the parallel plate capacitor?
To the right.
From the positive to the negative, or from the negative to the positive? Why?
That's how positive particle is.
Because if you put a positive test charge in here, it's gonna feel what from the positive plate? Repulsed, and it's gonna feel attracted, so that a positive charge would really wanna go to the right. But if you put an electron here, what would happen? As forget about this thing being negatively charged. As it left the positively charged plate, would it want to leave the positively charged plate?
No.
No, it's like, oh, I like you guys, so you're shooting a chihuahua out of a cannon.
Nice.
So not only are you shooting the chihuahua out of the cannon, what's the chihuahua going towards?
Other
More
chihuahua.
chihuahuas. So the chihuahua's going, ay, 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 okay? It's not going to like this, because it's leaving the safety of the St. Bernards, and it's going towards more chihuahuas. So fundamentally, we're trying to figure out how fast you shoot the chihuahua.
The speed of
So,
light, obviously.
what do you want the final velocity of the chihuahua to be?
Fast.
0. So what do you not know? So you're gonna have v squared minus, and then the square root of, so you're gonna have 0 minus 2. And this might not physically work out. I literally just made up these numbers. And a distance of 3 millimeters. 3 millimeters is 0.003 meters. Yeah, so you can make that like a negative acceleration.
Basically,
So I have no idea if this even works. So what do you get for your velocity?
7.72 e to the 7th.
At least it's less than the speed of light.
Yes,
That's why I said, this is gonna be bad if that number is like bigger than the speed of
we're
light.
getting there.
It's like, whoa, you're getting close, okay? You're 10 to the 7. Okay, so this is the kind of the thought process that you're going to be able to go through.
Yeah.
Okay, I know this week is kind of getting you jacked up. A lot of you have a lot going on with band and sports, so I'm done, okay? So your assignment is kind of gonna be almost like the review to a large measure. So, So there's different things I've got to give you. So just stay with me, because there's 3 parts to this assignment.
Yeah, it's 25. And what's 3? Yeah.
And yes, this goes old school spring.
About the mother chicken.
Yes.
Oh, sure. Yeah.
Well, then
They were saying that those grades and stuff.
you're doing it the wrong way. See, Cohen's got the right idea. What's funny is that he was also a part of it.
I was not a part of it.
No.
Okay, you're shocked.
Do it back the other way.
I was looking at this.
Just burn it. Yeah. That's not too bad. This is okay. Yeah.
Oh, yeah.
I was gonna say, it kind of feels like something we've already done.
Where are those problems though?
Surprisingly.
Yeah, this time it was not.
52, 54, 56. No, but 2, 4,
Okay.
Yeah, but it also equals O. Because we're storing the same amount of energy that the.
it's not too bad.
No, it's not.
I think if you take a
Except-
gravitational potential.
It's a log even, so you're gonna be losing your mind and you can't check it back in the book.
It's not too bad. 52. Wait, that you can smell it?
No, you just.
That's what he said.
Okay, okay.
He said he'd be able to smell it and he'd come into our classroom. That's what he said.
No, I just want to
That's what he
say,
said.
anyone would have smelled it.
Okay, let me explain the 3 parts to this assignment. So the first part are just the problems out of the book, okay? So that's gonna be part number 1. And this is the sequence that I kind of want this to work. So you got these out of the book, summation of everything that we've done. Yes, you gotta remember that the volume of a sphere is what? 4/3 pi r cubed. Just saying, you might need that. So that's gonna be the first part. Second part is going to be this problem right here. So what's going to happen, let me kind of give you a visual. You're going to take a spring, okay? And the first thing that you're going to do is you're going to hang it from a ceiling, and it has an unstretched length of 4 centimeters. I'm going to hang a 1 gram mass to it, and it stretches to a length of 5 centimeters. So what's your elongation? Do not make this difficult.
1 centimeter.
1 centimeter. When you graph force and elongation, okay, what should it be? Linear or nonlinear?
Linear. Serious? What? Linear.
It has to be F equals KX.
What?
It has to be a linear function,
Dang.
okay?
Oh, for force, not energy.
Wait, what's the unit?
I was
of
energy
energy?
of
I know
energy.
the energy.
Energy in joules.
Joules.
Force in
What's the slope gonna be? No, it's not Newton meters.
No, that's not what I mean. I was talking about something else.
joules per meter.
Newtons per meter, otherwise known as what variable?
Okay.
Lowercase k, your spring constant, right? Is the graph gonna start at 0, 0?
Yes.
Yes, because you don't have any force, you don't have elongation. At this point, you're gonna know 0, 0, and another point. Can you find the slope of the line?
Yes.
Yes. Can you find the spring constant then?
Yes.
Yes. Now, imagine I want to take that same spring, I want to put 2 charged beads on it. So, then it stretches to a length of 4.5 centimeters. What is the magnitude of the charge in nanocoulombs on each charge? Whoa. Now, remember, if you're gonna use F equals KX, what do you use? The length of the springs or the elongation?
Elongation.
But if you use F equals K Q1 Q2 over D squared, what are you gonna use? The elongation or the distance between the beads?
Distance between the beats.
Distance between the beads. Keep that in mind. Then, last thing you've got is this worksheet. Now, on some of these, it's just easier if you answer them right here. On C and D, you need to do some calculations. If you want to do that like over here, that's fine. If you want to do it on another sheet of paper, that's cool too. Just don't try and cram it in right there, okay? That's all I ask. If you want to do it on this, maybe put a little box, something like that. And yes, there is a question on the back, it's multiple choice. But here's the dumbest thing that you can possibly do, is that let's say you get to this question and you go, wow, I have no idea how to do this. And then you ask somebody, hey, what'd you get for that answer on that question? They say E. Okay, cool. And all you put down is E. You're gonna get 2 points on an assignment, and then you're gonna get the same question on the test with a lot of points and a large percentage of your grade, and you're not gonna know how to do it. Okay? So the worst thing that you can possibly do if you don't know how to do this question is just say, hey, what'd you get? Oh, just circle the answer. Okay? Not an option on the test. I'm just saying. Now, let's talk about that question on the back though. It says at which position will the electric field due to these two charges be zero? So let's just begin this analysis. Okay? So here's the origin, that's C, okay? And then you got negative Q over here, and then you got 4Q over here, okay? Now, you want an electric field, okay? Not a force, an electric field. How do you calculate electric fields in this situation? KQ over,
R squared.
is that Q what's fueling the field or what's generating the field? It's what's generating the field. So you got negative Q and 4Q. So let's say you think, hey, maybe that's going to happen right in between the two of them. Okay? Cohen, you shake your head with pain and disgust. Why?
Because they're acting in like the same direction.
Yeah, so is there any way, can you pick a point in between these two where the field could be zero?
No,
No, why?
because the fields are acting in the same
Yeah,
direction.
they're acting in the same direction. So you know your answer can't be in between the two of them. Okay? You know it can't be in between the two of them. So that means it's either going to be somewhere out here or somewhere out there. Okay, so these are your three parts. The problems out of the book, the spring problem, and then this sheet. And that's the sequence that you're going to hand these in. Okay, I'm done. So I know you have a lot going on. I'm giving you this time. Use it wisely. Okay? If you have not handed in the lab, I need it. Okay? All right, I'm done. You're on your own.
I don't know what order.
What order do you